Okay, we're going to look at some definite integrals, and these definite integrals, each one has an application for physics. Each one represents at least one very possible application. Okay, this function. Okay, now you can do the formula thing, equals, write your antiderivative with the bar and the upper limit and the lower limit. That's perfectly okay, but I want to emphasize what all that means. So, what's our antiderivative here? What's an antiderivative? Okay, well, any antiderivative will do, so we're not even going to bother to put the constant on the antiderivatives. Okay, an antiderivative of 2t cubed is what? T to the fourth over 2. So I'm going to say antiderivative we're going to use is t to the fourth over 2. Okay, antiderivative of t is t squared over 2, and minus 3 times that, we're going to have minus 3 halves t squared over 2 plus 4t. We could put a plus c out there, but as you almost certainly know, if we do, it's going to subtract off when we subtract the two values of the antiderivative. Okay, so what is the initial value of the antiderivative and the final value of the antiderivative? Well, that's easy to calculate. I'm going to go off screen and write those down. Okay, if I've got those numbers right, the antiderivative when evaluated for t equals 4 is 120, for t equals 7, 2392.25. Okay, that might or might not, all those significant figures might or might not be appropriate for the given situation, but since we don't know what the function actually represents, we include all the significant figures in this case. So the change is going to be this minus this. And that's going to be what, 2272. I do that right, 2272.25. So we say that this definite integral equals 2272.25, and we've reasoned it out in a way that uses the idea that the integral is the change in the antiderivative function. We'll see in a couple of minutes why that might be important. Okay, so next example, we have the integral cosine 2t dt between pi over 12 and pi over 6. This one is, numbers come out fairly simple. Your antiderivative can be taken to be 1/2 the sine of 2t, and that changes from what? Well, when t equals pi over 12, 2t is pi over 6. So, okay, well, 2 times pi over 12 is pi over 6, and you should certainly know that the sine of pi over 6 is 1/2, so this is 1/4. And it changes to what? 1/2 sine of 2 times pi over 6, and that's 2 times, that's pi over 3. The sine of pi over 3 is the square root of 3 over 2, as you should know, and half of that would be the square root of 3 over 4. So the change is square root of 3 over 4 minus 1/4, square root of 3 minus 1 divided by 4. And of course we can approximate this. Square root of 3 is approximately 1.732 divide that by 4, and that's equal to what? That's like 0.183. Okay. 4 goes into 72 18 times, and you're left with a 12 here, and you get to 3. So I believe that comes out in a fairly straightforward manner. Okay, of course I've written that result here. Now, antiderivative here. We don't have any numbers, we have just expressions. The antiderivative we have here, well, the negative GM is just a constant. But we're going to include that in the antiderivative. We're going to say the antiderivative. Actually, we have two choices. We can factor this out and do the integral of 1 over r squared dr and multiply that by negative GM. But I'm just going to go ahead and write out the antiderivative of this expression. I don't have this factored out of the integral sign, so we're going to include this as the function. We're going to include this within the antiderivative function. So the derivative of 1 over r squared is negative 1 over r, so that the antiderivative is nothing but GM over r. Very simple antiderivative. Of course, you can take the derivative of this function and verify that you do indeed have an antiderivative here. Okay, so the change in the antiderivative the antiderivative changes from GM over big R to GM over 2 times big R. And what's the change? The change is GM over 2 big R minus GM over big R, which equals what? Equals negative 1/2 GM over big R. Now, I was careless with my signs. There's a minus sign in front of this, so I'm going to have to change some signs. The antiderivative changes from this to this, so that the change is from this to this. So it's going to be this, which is negative GM over R, minus this, which is negative GM over big R. And you're going to end up with plus GM over 2R. Now, I haven't made the change here because I didn't have room. I'm going to have to make a couple of corrections. Okay, so gave myself a little more room to write all the negative signs there, and you can check out my algebra. Okay, so we get this. Now, I actually made that mistake. I'm not just pretending to make a mistake to make a point, but there's a point to be made, which is that, neglecting to write down my minus sign here, I got a result which I knew to be wrong because I know what the interpretation of this integral is. And we'll talk about the interpretation in a minute, but I'm thinking about the interpretation. I got down here and said, no, that can't be negative. That's ridiculous. Okay? So you do want to be careful. Okay, now let's look at one possible interpretation of each of these, of the first and the last integral. I haven't done an interpretation for this one because the interpretation would be a little more complicated, and I'm trying to keep things as simple as possible as far as understanding what these things mean. Okay, so in this case, if this 2t squared minus 3t plus 4 function represents a v of t, which I'm going to interpret as a velocity, so we're basically looking at velocity versus clock time, then when we integrate this, any integral represents the average value of whatever function is being integrated. multiplied by the change in your variable of integration, which would be the difference between these two quantities. Now you're not going to use that in calculating the integral because you don't know what the average value of the function is. So you're not going to use the 3-second interval here. You're going to evaluate the antiderivative at 4 seconds and at 7 seconds and calculate the change. But this does represent the average value of this function multiplied by the time interval, so that this represents average velocity multiplied by time interval. Now what do we get when we multiply an average velocity by time interval? Well, we get the change in position, or the displacement. I'm going to stick with change in position right now, so that this would be the change in position. Now we haven't put units on any of this, but once we do, we put compatible units on these quantities, and we're going to get a change in position in some system of units. Maybe in meters, maybe in kilometers, maybe in miles, maybe in centimeters, depending on what the units of your velocity function are, and your time function, your clock time. Okay, down here, this has a pretty specific meaning. Negative gm over r squared is the force per unit mass on a satellite at distance r from the center of a planet. Now I didn't have time or room to write everything, but let's understand that r's distance measured from the center of a planet. And actually I can draw a little picture to sort of depict that, so let me go off screen and do that. If this is our planet, this is the radius of the planet, then this is supposed to be double the radius of the planet. I think I got a little carried away. I went a little past double. But you get the idea. And the situation, typical situation would be we want to raise a satellite from here to here. Now, we don't just raise the satellite from here to here. We've also got to give it enough speed so it doesn't fall back and stays in orbit if we're trying to get a satellite in orbit. But in any case, this integral tells us how much work we got to do just to get the satellite from here to here, because the integral represents then the average force per unit mass. I didn't write that, let me correct that. Average force per unit mass multiplied by change in position, i.e. average force per unit mass, let me fix that one. Average force per unit mass multiplied by, in this case, r, because from r to 2r the distance is r. So that we would say, of course, we're moving from here to here. So this distance is r. And this is the energy per unit mass required to raise the satellite. Now I've chosen this because it fits with other interpretations done in terms of trapezoids. Okay, so if you understand those interpretations, you understand then what this integral is telling you, that 1/2 big G big M over R is the energy per unit mass to raise a satellite. More specifically, to raise a satellite from the surface to a distance equal to the radius above the surface. Interestingly, this is half the work you need to get from the surface all the way out to infinity. In other words, the energy that you would have to expend to escape completely from the planet. And though you aren't expected to know this right now, big M is the mass of the planet, and big G is the universal gravitational constant.